we should be able to do the first two together. Hopefully, are people on the web page where they have access to either the 2 atoms tab and the 3 atoms tab? Can they at least open that?
Yes.
That would be,
Which one do we choose again? The 2 atoms or 3 atoms?
we'll start with 2. We'll start with 2 because the first few questions are about the 2 atom screen, okay? So what I'm going to do is I'm going to use the Java app, because then we can do the 1 atom, the 2 atoms, 3 atoms, and then the real molecules. So that's what I'll share that. So for those of you lucky enough to have the, oh damn it, lucky enough to have the application, it would look like this. Come on. This is a pain. All right, can everyone see my screen with the application on it?
Yes.
Yes.
Okay, good, because I couldn't for a while. All right, fine. All right, so I'm going to go to 2 atoms. So the question is, list all the ways you can change the polarity of a 2 atom molecule. So I want you to have a look. There's 2 sliders here that you can see. So one of them is just atom A, and the other one's atom B. And you can control the relative electronegativity of them, okay? So if I choose, so right now I think the default is for atom B to have like medium electronegativity and for atom A to have very low electronegativity. And so what you can see is, what it gives you is, it shows you where the bond dipole is. And remember how we define the bond dipole when we draw the arrow. Remember, we have a little, we put an X where the partial positive charge is, so that this would be over the less electronegative atom, and the arrow would be pointing toward the more electronegative atom. Basically, the arrow points to where the higher electron density will be. It's sort of pointing at, who's going to be more negative, where the electrons are. So notice what happens as we move atom B. If we make atom B extremely electronegative, watch what happens to our arrow. It gets longer and longer. And basically, so what this is sort of it's a measure of the amount of the dipole. And anyone know how we can actually measure? There's a unit of measurement for the dipole. Anyone know what we refer to the measurement of the size of a dipole? You probably don't, but I mean, I was curious if anyone knew what it was called. We call it a moment. Like, let's take a moment, or they had a moment, or something like that. We call it a dipole moment. We measure it in something called Debye's, which always makes me laugh. So the larger the number of Debye's, the larger the dipole. And basically, this is just a measure of the distribution of those electrons along the bond. So if they're evenly distributed, then this would be 0, and there'd be no dipole moment. So look, the arrow, the size of the arrow basically reflects the size of the dipole moment. So with a big difference in electronegativity, the dipole moment is large and the arrow is long. And when we reduce the difference in electronegativity, it shortens up until when there's no difference in electronegativity at all, notice that there now is no bond dipole because the electronegativities are exactly the same. So click on the electron density under surface, and you'll see it's completely evenly distributed. There's no difference at all. One side looks exactly the same as the other side. But when I change the electronegativity of atom B, watch what happens. Notice that atom B gets darker and darker and darker, and the distribution of electrons around A gets lighter and lighter and lighter. And you can see it even better when you look at the electrostatic potential. Shows you. Now, the electrostatic potential gives you how much partial positive and how much partial negative charge there is. And so you can see this a little more easily. And when something's blue, you can see you have a partial positive electrostatic potential. What does electrostatic mean? We kind of know what electro means. Electro means electron. What is static? What's an electrostatic attraction? Basically, what does static mean? What is static? When you think of something, if something is static, what does that mean?
Is it like the friction we do with the balloon and the hair thing?
That's static electricity. That's right. But what does the word static mean?
Stable?
Not just stable. Something can be stable and not static. Static is a very specific meaning. If something is static, it's not doing something.
Is it like at rest or like
Yeah, it means it's not moving.
moving?
So it's either moving or it's static. So if something's electrostatic, that basically means it's an electric charge that's not moving. And so if I have a high electrostatic potential here, that means that I have basically a positive charge that's not changing. It's staying the same, it's static. And so it will be attracted to something else that has a static charge, like an ion, for instance. Like if I have a fluoride ion here, that would be attracted to atom A, because the fluorine atom has a static charge. It has an extra electron. It has a formal, what we call a formal charge. It has a whole charge, like -1, -2, -3. Those are called formal charges, right? And we talked about the difference between a formal charge and when we're writing oxidation numbers. We'll get more into that tonight. So in a covalent bond, you don't have a formal charge, but you have a partial charge. And so if you have a high electronegativity, you are pulling those electrons toward yourself. So B is a very, very high electronegativity. So this would have an electrostatic potential that's negative. And so it would attract something like a sodium ion, which is also electrostatic. And those would be attracted to each other. And this is, in fact, how water, for instance, attracts ions, how it bonds with ions. Because, and we'll look at water as one of the real molecules. Water has a partial negative charge around the oxygen, and we'll see how that works, and partial positive charges around the two hydrogens. And so it's this side that interacts with sodium. When you drop salt, when you drop table salt, sodium chloride into water, this is what happens. That ionic bond breaks, and then sodium then bonds with the partial negative side of oxygen because it's electrostatically negative. And the chloride ion, interacts with the electrostatically positive side of the water, which is the hydrogen side. And it's those interactions that basically replace the stability of the interaction between sodium ion and chloride ion. That's a strong interaction. Oh, there we go. But it's not as strong. But it's not as strong as all the interactions that water will make with sodium when it's free by itself and chloride ion when it's free by itself. Those bonds with water all added up together overcome are greater than the ionic strength of the sodium ion chloride ion bond. So let me clear that. So basically what we want you to do here is change the relative strength of atom A and atom B. Have a look and see what it does, excuse me, to the bond dipole. And then watch what happens when you turn on the electric field. When you turn the electric field on, it shows you how that molecule will then orient itself. Now what you can do is move this so that it points the other way, and watch what happens. That will only happen for a molecule that has a dipole moment. If, on the other hand, I make A equal to B as far as its electronegativity, I turn on the electric field and I move them around, nothing happens. So I can put this in whatever orientation I want, and it's not going to reorient itself because it doesn't have a dipole moment. It doesn't have a part of the molecule that has a partial positive and a partial negative side. It's completely uncharged, although it's completely even all the way around. So putting an electric field in there, electric potential, does nothing. And all I need to do is just change the electronegativity just a little bit. And then it reorients itself, okay? So basically the first thing we want you to learn on the 2-atom screen, basically list all the different ways that you can change the polarity of the 2-atom molecule, the diatomic molecule. And then it asks you just sort of to record your ideas about how does the bond dipole change as you change the electronegativity. So this would be the bond dipole here, right? So this is the bond dipole. How does that change as you change the electronegativity? And how do the partial charges change? And this, let me clear that. We haven't looked at the partial charges. This gives you the partial charges. And you can't see much of anything because the partial charges are so small. But watch what happens when I change the electronegativity of A. Those partial charges, see how they get bigger and bigger and bigger and bigger. So the partial charge gets larger and larger and larger as the difference in electronegativity gets larger and larger and larger. So what we say is that the molecule becomes more and more and more and more polar, until basically, if I have atom A with like the lowest possible electronegativity and atom B with the highest possible electronegativity, they won't be sharing electrons at all. That'll become an ionic bond. Because basically, as the electronegativity gets stronger and stronger and stronger, the fluorine, something like fluorine, is going to pull on those electrons and keep pulling and pulling and pulling. And it's basically just pull so hard that that pair of electrons will stay with fluorine. and the other atom will lose them completely, and that'll become an ionic bond. And you'll see something like if you have sodium fluoride. Sodium has a lower electronegativity than hydrogen. So the difference in electronegativity between sodium and fluorine is much higher than it is for the difference in electronegativity for hydrogen and fluorine. So this one becomes an ionic bond, and this one is a very polar covalent bond. Everyone follow so far? So are you able to do all these things on your computer, play around with them?
I have a question.
Sure.
What do you mean, list all the ways you can change the polarity? Like, as in, the electronegativity of atom A and electronegativity of atom B polarity, or are we talking about,
The polarity of the molecule. So because it's only a two atom molecule, if you change the electronegativity of the bond, you also change the electronegativity of the molecule because there's only a single bond. When we look at three atoms, it'll be different.
so in the list, do you want us to draw our like what we end up getting, like if we put atom A less and if we put atom B more?
Yeah, you can draw it. You can write it out in sentences. You can just do it in bullet points. However you want to do it.
Okay.
I'm just going to allow you to sort of express yourselves in any way you want. Actually, I never even thought of the picture. That's a great idea. If you just draw it in pictures with a little explanation, that's a really good idea. So basically, everyone's able to do this part because you don't need Java to do this part, right?
Yeah.
Okay, good. So even afterwards, you'll be able to go back and do this part. So why don't I I can sort of quickly go through two atoms and three atoms, then we'll spend more time with the real molecules, especially for the folks who can't do it. And so you can ask lots of questions as we go through it together. So let's look at three atoms. Because here we learn a really important lesson about the difference between a bond dipole and a molecular dipole. Anyone tell me what the difference is? How can there be a difference between a bond dipole and a molecular dipole?
Is the bond dipole between two, and molecular dipole is more of three atoms, creating
Well,
one.
it could be 4, 5, 6, 10, 50 atoms.
Three or more, creating the synergy to.
Yeah, I like that. I like that way of putting it. Creates a synergy. So what is it? What's the difference between? So does a bond dipole contribute to the molecular dipole, or is it different?
It contributes to it.
It contributes to it. In what way? So do I basically like add them together?
Yeah, for example, like A and C would contribute to B, which when they're all together, like
We have two. That's right. We have two bonds here. We have an AB bond, and we have a BC bond. So here's our AB bond here, and then our BC bond is on the other side. So can we just add them together? So if I have, let's say we'll just make up the number. So if I have like a polarity, let's say of 1, whatever that is, and I have a polarity of BC of 1, when I add them together, will my molecule have a polarity of 2? Can I just directly add them together like that? Or is there something else I need to take into consideration? Because you're absolutely right. So far, you were nailing it. Bond dipoles contribute to the overall molecular dipole. So my question is, is it simply additive? If I have like 4 dipoles in a molecule, let's say I have a 5 atom molecule with 1 atom in the middle and 4 of them around it. Can I just take all those 4 dipoles and add them together and get the molecular dipole? Same thing here. Can I just take A and B plus B and C and just add them together?
No, because isn't it you have to see if how it reacts to the other atom?
What do you? So yeah, you're onto something there. What do you mean?
Like if like fluorine, for example,
Mm-hmm.
it can only take 1 extra electron to share.
Right, but I'm talking about just these bonds. Let's say they're being. Let's say I have a very polar bond here. So this is very polar, and so is this. Does that necessarily mean that my overall molecular dipole will also be very polar? Can I just add them together? So if I have 1 polar bond plus another polar bond, automatically I'm going to have a polar molecular dipole as well. I'll give you an example. So let's say I have, well, oxygen, CO2, that's always a good one to use. So I have carbon in the middle, and I have oxygen on this side, and I have oxygen on that side. So we know oxygen is a lot more electronegative than carbon. So I've got a dipole going in this direction, and I have a dipole going in this direction. So I have 2 big bond dipoles. They're both very polar. So if I add them together, CO2 should be very polar as well, right? Because I have 2 really polar bonds. I add them together and I get so that must be a polar molecule, right? What do you think? So sort of what I'm getting at is, are these additive? So A is less electronegative than B. So we can say that AB dipole points toward B, right? And it looks like C is also less electronegative than B. So this has another dipole pointing toward B. Can I just add together the polarity of this polarity and this polarity? Can I just add them together and get the overall molecular dipole? Can I just do that? Or is there something else I need to take into consideration? So are the bond dipoles additive? Yes or no? That's sort of that's the basic question here. It's either yes or no. Who's got an opinion? Let's take a poll. How many yeses is how many nos? Can we just add the bond dipoles together? Actually, we can show them here because we can actually look at the bond dipoles as well. We just click on bond dipoles, it will show them. There they are. So can I just add these 2 together?
Yes.
Okay, I got a yes. Yeah, there's my 2 bond dipoles, because I just take that one plus that one equals this one. I have a yes. I'm going to keep track. Yes. How many no's? So I got one yes. Nobody else, very brave. Nobody else wants to state an opinion. Well, there's no wrong answers, just wrong people. Oh, come on. Someone must have an opinion. Not going to just have one vote. What do you think?
Yes.
Okay, 2 for yes. And yes is running away with it. I don't want spectators, I want participants. So I got 2 for yes, 0 for no.
No.
Okay, here we go. Now we're getting somewhere. We get,
No.
I'll say no.
and the no's coming into the woodwork now.
Yes.
It's even. Okay, as soon as one gets 5, we're going to call it off.
No.
No. Okay. We either need 2 more yeses or 1 more no. We're just going to sit here in silence and stare at the screen. Nobody wants to do that.
Yes.
All right, just 1 more.
Yes.
We probably even forgot what we're answering now. I got 1 more yes. I think I heard 1 more yes. Okay.
Yes, there's one more yes.
Okay, and the answer is no. So you 4 brave people that said no were correct. And the reason is, what do you think what other thing do you think we need to take into consideration other than, so the people who answered no, you can't just add those 2 dipoles together. What else do you need to take into consideration?
The electronegativity of the other atom.
Which other atom?
Because like I tried moving the electronegativity of atom A to more,
Mhm.
and then the molecular dipole goes with it if I move the atom C electronegativity to like.
But watch what happens. What happens to the bond dipole when you move? When A becomes more electronegative, watch what happens to it. It moves, right? What do you think's going on there? If I do the same thing happens if I change C to be more electronegative. The molecular dipole moves in that direction. I'll give you a hint. Watch what happens to the molecular dipole. Now remember, that's the one in gold or in yellow. That's the overall molecular dipole. So what it's telling us right now is because B is more electronegative than either A or C, I'm going to have more electron density up here, right? Because B is pulling electrons away from both A and C. So B is going to be partially negative. So if we click on partial charges, we see that B is partially negative, right? B is partially negative, and both A and C are partially positive, have a small partial positive down there. But, so that contributes to the bond dipole pointing up. so the points up toward B and away from from A and C, because A and C are partially positive, B is partially negative, so it points in that direction. But watch what happens. Now, I'm not going to change anything except the directions of the dipole. Now what happened? A is still partially positive. B is still partially positive. I mean, C is still partially positive. B is still partially negative. But there's no molecular dipole anymore. How come? Everything's the same. A is the same electronegativity, B is the same electronegativity, C is the same electronegativity, and they have the same partial charges that they did before. But now it's a nonpolar molecule. There's no, and a nonpolar molecule is defined as one that has no molecular dipole, and this has no molecular dipole. How did that happen?
Does it
When you change the shape?
I changed the shape. Very good. I changed the shape. When it was bent, we call this bent because, duh, it looks bent, right? That's bent. And look, the more bent it is, the greater that molecular dipole becomes. But when I make it linear, that molecular dipole disappears. Why? Why is the shape so important to the polarity of the molecule?
Because you're evenly distributing the charges.
I'm
Right.
not. I'm not. I have partial positive charges on A and C and a large partial negative charge on B. So it's not really the charges that's important. I mean, they're important, but there's something else happening.
Would it be the angle of the the angle of the structure?
The angle is very important. You notice that when it was bent, it had a molecular dipole, and now that it's linear, it doesn't. What happened to the bond dipoles? That's really what I'm getting at. What happened to the two bond dipoles when we go from it being linear to being bent? What happens to the two bond dipoles?
They
They
cancel each
stay
other out.
exactly the same size, but what's different about them? They're just the same size. We've done nothing to the bond dipoles. The bond dipoles are exactly the same as they were when it was bent. What has changed about them? The size of them has not changed. Something else has, though. So if we haven't changed, basically we haven't changed the intensity of the bond dipole. We've changed something else. What have we changed about it?
When it became linear, the arrows are pointing at each other.
Ah, and that seems to make a difference, doesn't it? So what if they're slightly not pointing? What if they're sort of slightly not pointing at each other? What happens? So now I've just changed it just a little bit. And what happens to the molecular dipole? So it's gone from being slightly, now I have a slight molecular dipole when they're bent slightly. What happened to the direction? So as someone pointed out, they were pointed directly at each other when they were linear. Now that it's not linear, it's slightly bent. Now I get a slight molecular dipole, and it appears that the size of the molecular dipole is dependent on how bent it is. Why is that? And if I bend it all the way, I get a huge molecular dipole. What's going on? What is it about the angle of the dipoles that tells us whether or not we have an overall molecular dipole or we don't?
90 degree?
Yeah, if it's at a 90-degree angle, we have a strong molecular dipole. And if we have a 0-degree or 180-degree angle, we don't have a molecular dipole. So what is it that we have to take into consideration? Not only the intensity of these two bond dipoles, but something else.
Direction.
The direction. So can we say if they're pointing in relatively the same direction, we get a molecular dipole? Because right now they're both pointing up, right? They're both pointing at B, but they're both pointing up. And so our overall dipole is up. Now I'm going to have them point down. And what happens to the molecular dipole? It points down. But what happens when they point in completely opposite directions? Now, when they face each other, they're pointing in exactly opposite directions. And what happens when they point in exactly opposite directions? So you can see that when it's linear, the two bond dipoles are completely opposite. They're pointing in opposite directions. One's pointing to the left, and one's pointing exactly in the opposite direction to the right. And so when they're pointing in opposite directions, what happens when you add them together?
Cancels out.
They cancel out. And that is the key to the whole thing here. Is when we add, these two things, when I asked you kind of a trick question at the beginning, whether or not the two bond dipoles are additive. And we had a poll, yes and no. And the answer is yes and no. Yes, if they're pointing in opposite directions, but no, if they're pointing in the same direction, they're additive, right? So I have a strong dipole between A and B. I have a strong dipole between C and B. If I directly add them together when they're pointing in the exact same direction, my molecular dipole is now twice as big. But if they're pointing in opposite directions, they completely cancel each other out. So yes, the bond dipoles are additive, but you need to consider the directions they're pointing in. Who's taken physics and knows what a vector is? Anyone know what a vector is?
Sort of.
Sort of is good enough. I'll take a sort of. So what's a sort of definition for a vector?
The direction? I don't know. Not
Yeah.
sure.
Yeah. A vector has two measurements. It takes into consideration two things. One, a measurement of size. So like how fast something's going or how much force something's pulling or something like that. But it also has a direction, right? So like for instance, speed just tells us how fast something's going. but velocity tells us which direction it's going as well as how fast it's going. So it gives you more information. The same is true here. These dipoles have two things you need to take into consideration. One, how big they are, and two, what direction they're in. So they're only additive if they're pointing in the same direction. So, and the more they're pointing in the same direction, the more additive they become. So you can see we can have two large dipoles. Here, I'll make B extremely electronegative. So I have these two really big dipoles. You see that it gets smaller and smaller and smaller the more and more and more they start pointing in opposite directions. So we need to consider two things: the size of the dipole and the directions of them. Because notice the partial charges do not change. So just because I have a molecule with very, very polar bonds in it and the electrons are not evenly shared, if C looks exactly like A, if I take that molecule and I flip it over and it still looks exactly the same, basically it means it's symmetric, right? This molecule is symmetric. And if I turn on the electric field, I guess I haven't got it exactly. Here we go. Yeah, now it's completely, I've got them completely opposite. Notice it's not polar. I can spin this around all I want and it will not change. So the electric field can be on or off. It stays in the same orientation because it's symmetrical. Now, if I just bend one of them just a little bit, it's no longer symmetrical. There is slightly more negative charge on the top of the molecule, and the top of the molecule would now be here. This is now the top of the molecule and would have slightly more negative charge on the top. This would be ever so slightly negative. And this now becomes the bottom of the molecule and be ever so slightly positive. But if the middle of the molecule is positive, or the middle of the molecule is negative, and the outsides are exactly the same positive, it's completely symmetrical, and therefore it doesn't have a molecular dipole anymore. Does that make sense to people? Basically, we're looking for if something's symmetrical, if something's completely symmetrical, it does not matter what any of the electronegativities are. If it's completely symmetrical, oops, that means it's the same all the way around. Either it's, okay, does that make sense?
Can you explain about the size again of how it affects the molecular dipole?
Oh, sure. If I have if I make these two dipoles smaller, let's make this, okay, here we go. Now we have a big molecular dipole, right? You can see that yellow arrow is now very, very large, and I have a bent molecule. But if I make these two bonds less electronegative, that's the overall size of that molecular dipole goes down. Because in this instance, we're not changing the angle, we're changing the absolute size of the bond dipoles. And if the absolute size of the bond dipoles goes down, the overall size of the molecular dipole also goes down. It'll keep going down until basically I get rid of the dipoles completely. And now I have three really electronegative atoms, but they're all sharing electrons equally. And my bond dipoles and my molecular dipole disappears. So for a molecule to be polar, it needs two things. it needs polar bonds. You can't have a polar molecule without polar bonds. So I need to have bond dipoles to make a polar bond. That's essential. The other thing I need, though, is that it can't be symmetrical. It can't be symmetrical. In other words, I can't have these bond dipoles cancel each other out. Now, I have a completely symmetric molecule. A and C are exactly the same distance away from B, and they're exactly the same angle from B. So I can flip this around and it looks exactly the same. So ABC looks exactly the same as CBA. It's identical, it's symmetrical. And so once things are symmetrical, I no longer have polarity of my molecule. I have polarity in my bonds, they're polar, but my overall polarity of the molecule is now gone. So a polar molecule needs two things. It needs polar bonds, so there needs to be a difference in electronegativity, but those polar bonds need to point not in opposite directions. They need to point in the same direction, either up or down. So those are the two things you need, okay? Does that make sense? And so since you have access to this one, play around with that and see the sort of do what we've been doing here. Look at what makes up a polar molecule. Can I have a polar molecule? And you check on whether or not you have a polar molecule by turning the electric field on. If you have a polar molecule, it will orient in the field. And if it's nonpolar, it won't. And so you can see here, we have two polar. Oh, go ahead.
I have a question. If I change the order, like let's say there is an option to put A in the middle, or no?
No, but you can change. Let's say, for instance, I make A more electronegative. Watch what happens.
No, I mean if I put A in the middle, in the center.
You can't do that, but you can change. You can make B more. You can change the electronegativity of any of them. So you can make the electronegativity of these three whatever you want. But what I sort of want to point out here. So I have a nonpolar molecule because for two reasons. My bond dipoles are exactly the same size and they're pointing in exactly opposite directions. But watch what happens when I change the size of just one of the bonds. I'll tend to be more dramatic. I'll show you the other side. I'll change C and watch it flip. So now it's no longer the same. It's no longer symmetric. Why? It looks symmetric. I mean, if you look at the molecule, it looks symmetrical. But let me just look at the two bond dipoles by themselves. The two bond dipoles are now different. One is gone. So here, if I make one of them much, much smaller than the other one, then it will disappear. So basically change, you can see you can change the size of these dipoles relative to each other, and it changes the orientation. Okay? So if I make this now more electronegative, even though they're pointing in the same direction, one of them is bigger than the other one. And so you need to take into consideration for a nonpolar molecule that has polar bonds, not only do they have to be pointing in the same direction, they have to be exactly the same size. And that explains why CO2 is nonpolar, because the polarity of this carbon-oxygen bond is exactly the same as the polarity of that carbon-oxygen bond. They're exactly the same. But if I change this to nitrogen, if I made that nitrogen, it's no longer symmetrical because the size of those two dipoles is now different, and so now it has a net polarity where before it didn't. So the way we refer to the molecular dipole is basically the net polarity of all the bond dipoles added together, taking into consideration two things: the size of them and the shape of them. So that's why the shape of the molecule is just as important in determining whether it's polar or not as the bond dipoles. Is that clear for everyone now? Hopefully.
Professor, I have a
Yeah.
question.
Okay.
Symmetrical, I tried playing around with it when
Mhm.
I moved a atom A to less electronegativity, and then C is more,
Mm-hmm.
and it's linear. There's still a molecular dipole. It points the same direction. So
Right.
is that possible?
So if you make, so in other words, you made A less electronegative. Is that what you
Yeah.
said? Okay. So
Yeah.
A is now less electronegative, and
And
C
then
is more,
yes, and then B is in the middle.
and B is in the middle. We're making C more electronegative. So C would have the same electronegativity as B, basically?
No, I made it to the maximum for
Okay.
then B is in the middle.
Okay. Yeah, I still have a molecular dipole. Because now those two bond dipoles are pointing in the same direction. The AB bond dipole is pointing this way, and the BC dipole is also pointing that way. It's smaller, but it's pointing in the same direction. So basically, we can just add them together. So we can just add AB and BC because they're pointing in exactly the same direction. So my molecular dipole would be also pointing in that direction and slightly bigger than either one of them because they're additive.
Oh, so you can add the bond dipoles when they're in the same direction?
Oh, definitely. Yeah. I mean, if I make like for instance, the original one we had here. So I just basically adding AB. So the size of AB and BC are both the same size, right? But notice when I look at the size of the molecular dipole, it's basically twice as big because I've added them together. Because if you add two vectors pointing in the same direction, you basically get a vector twice the size pointing in that same direction. And that's what we've got here. So I've got two bond dipoles, both pointing towards C. And so this is not a this is not a molecule that's the same all the way around. Because let's look at the partial charges. A has a partial charge of positive partial charge, and C has it's a negative partial charge. So it is not symmetrical. Or symmetry is gone because one is positive. Now I have a positive side and a negative side. So by definition, that's not symmetrical. Okay. Let's look at you guys can play with 2 and 3. I just want to look at some of the real molecules so you can answer some of those questions. Okay. Do we have any more questions about this before we go on?
I have one question.
Sure.
You didn't finish when you were saying about the polar molecule. You were saying
Mhm.
something about how it'll orient itself in the electric field in order to.
Yes. So a polar molecule will orient itself. A polar molecule, by definition, has a molecular dipole. And in this instance, that's where the molecular dipole is pointing. So remember, we make the arrow points toward the negative side of the molecule, and we have a little positive sign that's on the net positive side of the molecule. So here, this tells us that the A pointing towards A is the positive side, and pointing towards B is the negative side. So when we turn the electric field on, C as being the negative side will orient toward the positive. Now, if we flip these two around, it flips. So now A is the more electronegative element than C. And so A is going to be partially positive, and C is going to be A is going to be partially negative, and C is going to be partially positive. And so it orients itself. And if we make our original, where they were both lower, so now it doesn't have a molecular dipole. But if I change the direction, now it does. So if the two bond dipoles cancel each other out completely, pointing in opposite directions, no molecular dipole, not polar. But if I change it even slightly, the direction in one way or the other, and you can, do this for yourself. If you change it even slightly, I now get a molecular dipole, because those bond dipoles are pointing in the same, even if it's just slightly pointing in the same direction. I now will have slightly more negative charge on this side of the molecule. That'll be slightly negative, and slightly more positive in this pocket over here will be slightly positive. And so it will orient itself directly like that. Okay? Any other questions before we go look at some actual molecules? There's a bunch of them. There's a couple of important ones to consider. Just look at some real molecules. So let's look at water. Where's water? It's got to be in here. So here it is. So there's water. So let's look at the bond dipoles. So it makes sense that they're both pointing right through oxygen. They're both pointing towards oxygen, because hydrogen is less electronegative than oxygen is. So if you label, you can also look at the atom electronegativity. So we can see here that oxygen is like the second highest one, 3.5, and that hydrogen is sort of right in the middle. It's like 2. And so these are very, very polar bonds. You remember, any difference bigger than like 1.8, I think, is considered ionic. So this is like bordering on ionic. So they're very, very polar bonds. But they're both pointing towards oxygen. And so if there is, because water is bent, and we'll learn why that is, because water is bent, they're both pointing up. Somewhat. They're not pointing directly up, but they're both pointing up. So when we look at the overall molecular dipole, it points strongly up towards oxygen. And you can see when we look at the electrostatic potential, oxygen is highly negative, and the hydrogens are highly positive. Not completely, but pretty close. And if we look, and we could keep going, we could keep adding all kinds of information here. The partial charges, you can see that oxygen is almost a whole negative charge to itself, because it's stealing electrons from both of the hydrogens. Both H1 and H2 are losing electron density to oxygen. So each of those bonds, so now we have a total of 4 electrons rather than just 2, because there's 2 bonds, right? And those 4 electrons are being pulled towards oxygen. So much that it almost has a complete negative charge to itself. So that's why water is extremely polar. And you can see it just by looking at the distribution of the distribution of the electrons, the electrostatic potential. Oxygen, very, very negative, almost complete charge. And the hydrogens, both about a third of a charge. So that side is positive, the other side's negative. Any question about why that is? I mean, we'll learn why it's bent, but just looking at it, you can see, you can sort of understand why the polar dipole is so strong and pointing toward in the direction of the oxygen. Is that clear to why that would be? We have two things happening. We have two very polar bonds. So remember what I talked about, why some things are polar. You need two things. You need a polar bond, right here, very polar bonds. And two, they can't be pointing in opposite directions. And you can see here, they are not pointing in opposite directions. They're both pointing up. Oxygen is up and away from the two hydrogens. So the molecular dipole points up and becomes very, very polar. Any questions about water? We're going to return to water a bunch of times because it's, you know, it's the most important molecule on the planet and everything. So I'll keep coming back to it. Any questions right now about it?
Can you actually repeat what you just said about the oxygen being higher than the hydrogen?
Oh yeah, they're not in a line. Notice they're not in a line. I don't have hydrogen, oxygen, hydrogen. It's not linear. It's not a linear molecule. So basically, on one side of the molecule, I have oxygen, and on the other side, I've got hydrogen. They're on opposite sides, right? Because they're not in a line. If they were in a line, we wouldn't have opposite sides. One side would be exactly the same as the other. But since they're bent, I now have opposite sides. And oxygen is a lot more electronegative than hydrogen. So I have two sides of a molecule now because of its bent nature. I have an electronegative side that's very highly electronegative. So I have a lot of electrons on that side. And on the other side, where I have my hydrogens, not so electronegative. So partially positive because it's missing electron density. And so it's because I have sides of the molecule that A, it's not symmetrical, and B, it's now polar because I have sides that are different. And that's basically all polar means. I have different sides. Because of the shape, I have different sides of the molecule. In water, I definitely have two different sides.
Okay, thank you.
Okay, yeah, let's look at another one. You can see it's sort of the same kind of thing. I think ammonia is in here. All right, let's look at ammonia. Is ammonia? Yes, ammonia is in here. So ammonia is also polar. Ammonia mixes together with water, and they mix together very well because they're both polar. Let's look at ammonia. So with ammonia, we have nitrogen in the middle, and we have three hydrogens around it. What do you notice about the three hydrogens? Is it symmetric? Is this molecule symmetric? I'll just ask that question. Is this a symmetrical molecule?
No.
No.
No, it isn't, is it? We sort of, because notice those hydrogens are bent. They are not sticking straight out. If they were sticking straight out, we would see something like this. We'd have nitrogen in the middle, and we'd have 1, 2, 3 hydrogens in a plane, right? This would be, and we would call this a planar molecule because it's flat. This isn't planar, is it? It's sort of, it has a three-dimensional shape with hydrogen sort of on the bottom of it and nitrogen on the top. Would you say that that's true? That it's sort of, it's three-dimensional in that way? It's not planar? Well, you could say it or you wouldn't. So you know what I mean by planar, right? So basically it would be flat. I'd have hydrogen in the middle, and I'd have nitrogen in the middle, and I'd have 3 hydrogens coming out, and everybody would be in the same plane. It would be completely flat. And if the molecule is completely flat, one side of it would be exactly the same as the other side. The top and the bottom would be identical. And so it would be symmetric. Therefore, it would be nonpolar. But since the 3 hydrogens are not symmetric and around, you see they're sort of bent. They're on the bottom of the molecule, and the nitrogen is on the top. Let's look at the electronegativities. Now we see that nitrogen is almost as electronegative as oxygen. Not quite, but it's almost as electronegative. So these bond dipoles are not going to be quite as strong as the water was, because water had oxygen hydrogen dipoles, and these have nitrogen hydrogen dipoles, so slightly smaller. But instead of 2 of them, how many do we have now? How many bond dipoles do we have now?
Three?
Yeah, now we got 3. So with water, we just had a single oxygen in the middle, hydrogen on one side, hydrogen on the other side. We had 2 bonds, so 2 bond dipoles. But now we have 3. And now when we look at the molecular dipole, it's pretty much the same size as water. Why? We have weaker bond dipoles, but we have more of them. And they're also pointing towards nitrogen slightly. So when we add them all together, we also get a very strong overall molecular dipole pointing toward the more electronegative element, which is, in this case, is nitrogen. So therefore, ammonia is almost as polar as water. And let's look at the partial charges. Now, since nitrogen is basically, I'll just take some of these out so you can see. You can see that nitrogen, because it has 3 hydrogens that it's stealing electron density from, basically has a charge just to itself. So it's very negative. So if we look at the electrostatic potential, it's highly negative on the top where the nitrogen is, and quite positive on the bottom where the hydrogens are, because of the shape. If it was completely planar, if it was completely flat, those 3 bond dipoles would all be pointing at nitrogen, and they'd all 3 be pointing basically in the same direction to cancel each other out. Now they don't cancel each other out. They're pointing slightly up, and so they reinforce each other. And so that's why nitrogen is very negative and the bottom is highly positive. Does that make sense to everybody?
Yes.
Yeah, it really shows you that the shape is super important. That's basically what we're going to be talking about tonight, why the shape of molecules is so important. So we'll be learning why molecules are the shape they are, and B, why that shape influences some of the chemical characteristics. Why do you think this? Why do you think this is bent? Anyone have any sort of ideas about why this would be bent? How come? What's up here? Basically, I'm just going to ask. I'll put it that way. What's up here that's making those bonds be bent? Why isn't it planar? I mean, it should be, right? I mean, if I just look at it, I don't understand why it's not planar. That would be because every molecule basically wants to be in the lowest energy state it can, and having it be planar would be lower energy. How come it isn't planar? There's something up here that's making it not be planar. You know what it is?
A lone pair.
Exactly. It's not empty space. It looks like it's empty space, but it isn't. There's actually a pair of electrons up there. That's the pair of electrons that nitrogen keeps to itself. So remember, nitrogen is in group 5. So it has 5 valence electrons, 3 that it shares, 1, 2, 3, and 2 that it keeps for itself. And these are the 2 that it keeps for itself up here. And a pair of electrons in space, in that particular orbital, is very negative. You have a pair of electrons together, that's a lot of negativity. And it basically pushes these other bonds away from it. Because remember, what is a bond? A couple of electrons. That's all a bond is. And so one pair of electrons coming into close proximity with another pair of electrons, they push each other away. And so a lone pair of electrons pushes those other pairs of electrons, which are bonds, away from it. And in this instance, instead of them being linear or being flat in a plane, it pushes them away. And so now we get bent. And the same thing is true with water. But instead of having one pair of lone pair, it is 2. And so pushes those hydrogens away even more. Excellent answer. So yeah, let's have another look. Let's look at another one. Okay, here we go. This will. Boron trifluoride. So this looks like ammonia in a way, right? We have a central atom, and we have 3 atoms around it. But what's different about boron trifluoride? What do you notice that's different about it?
The size of boron is bigger.
Fluoride, yep, fluoride is bigger than hydrogen, definitely, and it's more electronegative. So instead of the bond dipoles pointing towards the central atom, let's look at it. They're pointing away from it. You see, they're all pointing away from boron. Now, so that's very good point. So two things. 1, fluorine's bigger than hydrogen. 2, fluorine's more electronegative than hydrogen. And so the bond dipoles are pointing in the opposite direction. What else do you notice that's different about it?
There's no molecular dipole.
How come? Yeah, I haven't even shown you that. You obviously you were able to look at it. Yeah, there's no molecular dipole. Why? Look at the electronegativities. Fluorine is 4, and boron is 2. So those are extremely polar. Those are like ionic level of polarity. But there's no molecular dipole. How come? I have 3 extremely polar bonds, but no molecular dipole. Why is that? What's different about the shape? Compare what we just looked at with ammonia and compare that to the shape of boron trifluoride. What's different about the shape?
The shape is in a planar structure.
That's exactly right. BF3 is planar, meaning all of those atoms are on the same plane. And when it's planar, it's flat. So this molecule is completely flat, meaning there's no top and there's no bottom. It's completely flat. And it's completely symmetrical. Notice, basically it looks like a fidget spinner, right? We could just spin that thing. And it's the same, we have the same bond angle. Each one of those has 120 degrees because there's 360 degrees in a circle. So each one has exactly the same bond angles. They have exactly the same bond angle. They have exactly the same size of dipoles. And when we look at the bond dipoles added together, let's have a look. They're all pointing away, but notice they're pointing at 120-degree angles from each other. And so when we add them together, what do we get? Basically, if I take this arrow and that arrow and that arrow, and I add them together, what do I get?
Zero.
Zero. Yeah, right. Because they're completely symmetrical. Just like these two arrows are completely symmetrical. When I add them together, I get zero. These three arrows are completely symmetrical. So when I add them together, I get zero. Basically, anywhere with there's symmetry, when I add everything together, I'm going to get zero because it's the same all the way around. So what I'm going to have is boron in the middle is going to be slightly positive charge to it because it's not nearly, and let's have a look and see how bad the partial charges are. I bet boron is just suffering. Yeah, so boron basically almost is a full positive charge. And the three fluorines are slightly negative. The only reason that boron isn't completely positively charged because it has three fluorines pulling in opposite directions. If they were pulling in the same direction, boron would just not have a chance. But since they're pulling in opposite directions, they basically keep it from being completely positively charged. So it's completely symmetrical. We have three very, very polar bonds. But since they're symmetrical, when we add them together, we get zero as a molecular dipole. So would this be a polar molecule or a nonpolar molecule?
Non-polar.
Nonpolar, right. And the reason is nitrogen makes 3 bonds. So nitrogen makes 3 bonds, right? And it has a lone pair of electrons. What group is boron in? Anyone remember? How many valence electrons does boron have?
3.
3, very good. And where do you think they're going? One of them's going here, one of them's going there, and one of them's going there. They're in 3 different bonds going in completely opposite directions. And it doesn't have a lone pair. So if it doesn't have a lone pair, it doesn't have a lone pair either on top or on the bottom, pushing those BF bonds away from it. It's not pushing those shared electron bonds away from it. And so if it's not pushing them away, remember I said every molecule takes the most stable shape it can. So the most stable shape this molecule can take, with these bonded electrons being as far away from each other as possible, is 120 degrees in a plane. Any molecule, and we'll talk a lot more about this tonight, what any molecule wants to do to achieve stability is to get those unshared pairs of the central atom and the shared pairs in bonds as far away from each other as they possibly can be, because electrons are negative and they repel each other. And so every molecule shape is basically dictated by how far away these electrons can get from each other. That's why this one is linear with 120 degrees. And that's why when we looked at ammonia, look at ammonia again. When we looked at ammonia, it's not linear because what we can't see here, but what is actually here, is a pair of electrons on the top. And that pair of electrons forces the other pairs of electrons, which are in bonds, away from it. And so this makes an angle closer to like 109 degrees, which is the angle you would see at a pyramid. And so we're going to be talking a lot about these different shapes, different bond angles, and how they affect the overall polarity of molecules. Shall we look at one more before we go?
Yes, please.
Okay. All right, cool. Well, actually, I'll let you guys decide. So I'll just pull down the menu. You just tell me which one you want to look at. So I mean, all the diatomics are going to be fairly straightforward. None of them are going to be. Why are none of the diatomic molecules going to be polar? Hydrogen, nitrogen, oxygen, fluorine, none of them are going to be polar. Why is that?
Because
Think about where, oh, go ahead.
they are symmetric.
One reason, they're symmetric. What's the other reason? Remember, there's two things you need to be polar. You need to be asymmetric, and what's the other thing you need?
The size.
Size of what? You're onto something. Something needs to be there. It needs to be asymmetric, but something else needs to be present for it to be polar.
Bond dipoles
You need bond dipoles. And how do you get bond dipoles?
by polarity.
Yeah, well, how do you get them? What tells me whether a bond is polar or not? Remember, it's different. Go ahead. Sorry, interrupted you.
Difference in the electronegativity.
Exactly. So you need to have a difference in electronegativity. But what's the difference in electronegativity between hydrogen and hydrogen?
It's the same.
So the difference is what?
0.
0. Therefore, nonpolar. The difference in oxygen and oxygen?
0.
Difference in fluorine and fluorine?
0.
0. So any diatomic molecule is nonpolar by definition, because there's no difference in the electronegativities of them. They could be extremely, like fluorine is F2. So yeah, they're both super electronegative, but they're the same, so there's no difference. So every diatomic molecule is nonpolar, and they're all gases because they're extremely nonpolar. So they're all going to look the same. The only difference is they're just in size will be the only difference. So we've looked at some 4 atom molecules. You want to look at a 5 atom molecule? You guys can decide. Which one should we look at?
Tetrafluoromethane.
Okay, cool. All right. Tetrafluoromethane. Let me turn off the bond dipoles, the partial charges. You guys could tell me whether you think it's going to be polar or nonpolar. There's what it looks like. There, the atom electronegativity. So carbon is 2.5 and fluorine is 4. So our difference in electronegativity. So the difference in electronegativity, and that's how we're always going to put this with a delta. Just a little triangle. Delta means difference. Our difference in electronegativity is 1.5. So it's a very polar bond. So the bonds are very polar. So we have polar bonds. So that's our first criteria has been answered. You can't have a polar bond. We can't have a polar molecule without polar bonds. And boy, oh boy, we got polar bonds here. So that's not a problem. But the question is this going to be a polar molecule or not? What do you think? Before you click on anything, what do you think?
No.
Have a look at the shape. No. Okay. Why? You say that with actually with some confidence. Why do you think that's true?
Because it doesn't have a lone pair.
Carbon doesn't have a lone pair. Excellent point. Yeah, carbon is in group 4. And remember, when we write the Lewis structure, and we'll talk more about that tonight, when we write the Lewis structure, we go 1, 2, 3, 4. It makes 4 bonds and does not have a lone pair. And so I'm going to keep grilling you because it doesn't have a lone pair. What does that mean for the shape of the molecule?
It's linear.
Does this look linear?
I mean, no. Well, isn't it going to be symmetric?
Yes, it is going to be symmetric. Exactly. There's no lone pair. And so these 4 fluorine atoms, so here's our fluorine atoms. These 4 fluorine atoms are going to situate themselves as far away from each other as they possibly can, because those shared electrons, remember, are negative. So each of these bonds, we got 4 of them. We got 1, 2, 3, 4. Each of those little pegs or sticks is a shared pair of electrons. It's a bond. They're going to move away from each other as far as they possibly can. And so this particular shape we call pyramidal. It's not planar because we have 4. And so if we put 4 in a plane, we would get, each of these angles would be 90 degrees. And we could actually set up a different shape where the angles are greater, and so they can move further away, and that's in a pyramid shape. So it's completely symmetrical. It has very polar bonds. What is the molecular dipole going to look like?
There isn't one.
There isn't one, right? There isn't one. So we look at the bond dipoles. There they are. If you can't really see that terribly well, but yeah, the bond dipoles are all pointing away from carbon and toward the fluorine. And that makes sense because fluorine is tele-electronegative, remember. It's always going to point toward fluorine. They're all pointing toward fluorine, but again, they're all pointing toward fluorine at an angle of 109 degrees. Each one of them basically completely symmetrical, pointing away from carbon at the same angle. And just like when we added these 2 and got 0, and we added these 3 and got 0, this time we're going to take 1, 2, 3, 4, and out of plane, which is kind of a little difficult for me to draw, but all of these angles are completely the same. So I have all the same size arrows, and all the angles are completely the same. So when I add those together, I also get 0. Yeah, very good. So you can see the carbon is almost as a charge, I think, in this one. Oh, no, right, because it's being put. So carbon is like about positive 0.42, and all the fluorines are like slightly negative 0.11. Slightly negative because there's 4 of them, and they're all trying to steal basically from carbon through each other. And so it's kind of hard for all 4 of them to pull. If there was just 3, actually now for the last one, let's look at the difference. Let's change one of these fluorines to hydrogen and see what happens. Let's do that one next. So here, I'm going to take all these out. All right, so let's change one of these to hydrogen. Now, I no longer have 4 fluorines. Now I got 3 and a hydrogen. Notice, what is it about the shape? Is the shape the same as when there were 4 fluorines?
No,
It isn't?
different.
It's different? I'm asking about the shape. I mean, yes, the molecule looks different, but is the shape the same?
Yes.
Yeah, I mean, the shape is substantially similar, right? I mean, it may not be exactly, and I can tell you for a fact that these bond angles are slightly different, but the overall shape is pretty much the same. I mean, it still has that pyramidal shape, right? So the shape is pretty much the same. But what about the bond dipoles? Are they going to be the same? You suspect the bond dipoles will be just the same as the previous molecule when all four were fluorines?
No.
No. Right, one of them is going to be weaker, right? Because we know that the bond dipole, let's look at the electronegativities. So carbon and fluorine, that points towards the fluorine. But a carbon-hydrogen bond, carbon's actually slightly more electronegative than hydrogen. So carbon-fluorine is going to point in this direction, but a carbon-hydrogen is going to point toward the carbon. So it's different. So now we have one bond that's different. So let's look at the bond dipoles. So basically we have three bond dipoles all pointing towards the green fluorines. So let's just label the fluorines so you can see them. So we have F1, F2, F3, the three fluorines. And you can see that those bond dipoles are pointing toward the fluorine. But what about the hydrogen carbon dipole? What direction it's really hard to see. But can anyone see what direction it's pointing? Or what direction is it supposed to point in? I'll put it that way.
To carbon.
Yeah, exactly. It's kind of hard to see, but yeah, that little dipole there is actually pointing toward carbon. So we have three dipoles, three carbon fluorine dipoles, all pointing down, right? They're now pointing down. And we have another one on top that's also pointing down. What's going to happen to the molecular dipole this time?
Pointing down.
It's right. So when we look at the molecular dipole, it points down. Now we have a polar molecule pointing down. And so when we had CF4, we had four fluorines surrounding carbon. It was a non-polar molecule. And that's actually a gas. We replaced just one of those fluorines with hydrogen. It's now a polar molecule. And this is a liquid. All it took was changing one atom whose electronegativity was different, and that changed the whole thing, because we had four dipoles pointing in opposite directions. We just take one of them away, it's no longer symmetrical. And the minute you lose the symmetry, it now becomes polar. Okay? And you can see that when we look at the electrostatic potential, look. We now have a positive top and a negative bottom. So now we have polarity. So take another few minutes to answer some questions, and then you guys can play with these yourselves. And tonight we'll go over how to draw some of these. So even if you can't use this particular part of the simulation, you'll be able to draw it yourself and then be able to make the same conclusions. So basically, I want you to be able to draw the bond dipoles, see which directions they go in, and how they affect the overall polarity of the molecule. So any questions before we wrap this up?
So how can we do the lab report? Just answer these questions?
Yeah, basically I just sort of laid it out so you can answer the whole thing right on the sheet itself. I even included a last page to write conclusions. So you can just fill out the sheets. So there'll be a lot of drawing, just like it'll be very similar to the recitation we're going to do tomorrow. Basically, we're just going to be learning how to draw the Lewis structures and then converting Lewis structures into overall shapes. I'll have the office hours tomorrow and Thursday to answer questions on this. So you can do the first two yourselves. The third one, either you're just going to have to draw them yourself or try and find a nice person who has Java and try and Skype with them or something. Yeah, sorry about that. I'll try to avoid doing Java in the future. I realize it's going to be problematic for those of you with Macs. Macs just don't trust anybody. Sort of, that's the way they've always been. I was a Mac user back in the day. Any questions before we go? That's a lot of information. Just want to chew on it for a while, it sounds like.
I have a question with the lecture exam on Friday. What time are you going to be posting it?
Same time. I'll post it at 10 and you'll have till Saturday at 10. Yep.
Okay.
Is it also a PDF as well?
Yes. And remember, if you don't have to print it out. You can just answer the questions on like just loose leaf or something. That's fine. You don't need to print it out.
Another question is it similar to the recitation, the lecture?
Yes, it'll be similar. Yeah, the questions will be very similar to the recitation type questions or the examples that we do in class together during lectures. Very similar to those. What I would do to review is, review those questions. Also go to the text, because in the textbook, I think every other answer is given in the back. So you can basically you can do the question, then check your answer.
Another question is,
I often take questions from the book, just saying. Yes.
I have a question. Is there any writing answer, like explain or writing question?
Definitely.
Not only like calculation?
You're afraid I'm going to ask you to think?
No, I mean like from the lecture, like if you ask what is the definition, what's the different, you're gonna ask this.
Yeah, I can ask questions like that. I think that's fair.
Okay. And it's gonna be long?
Yes. Long and hard and just terribly difficult. Yeah. No,
I
it'll be
have
fine.
a question.
Yeah.
When do we hear back of our lab? Is it a week or 2 weeks?
But the lab exam?
Mm-hmm.
Oh, they're being corrected even as we speak.
Oh, wow. Okay.
Yeah. Dr. Gagreb has stepped in and been a champ, but he's grading them right now.
Oh, okay.
Another question, Professor, for the exam on Friday, we have to study recitation, the first recitation until recitation number 5 or 4?
I don't know which one starts in chapter 4. So I think it's the first 6, or all chapters 1 through 3, right?
Mm-hmm.
Yeah. So basically all of them.
So it's chapter 1 to 4 is the lecture. Right?
Except the last one. The last one had quantum numbers and stuff. That won't be on there. Oh no, it will be on there. Never mind. Yeah, because we just barely started chapter 4. So basically everything up, basically all of them.
Oh, will you also be uploading the recitation, the past recitation answers so we could compare?
We've got the first 4 up there.
Oh, you already got it. Okay.
Yeah, people are still sending them in. So we'll put the first 4 up there for you.
Okay.
Yeah.
And
I
are you
did.
able to upload the
Video.
video for chapter 4, the beginning?
The videos, yes, I've got those edited, and I was just waiting to sign off because it takes so much computer power to send them to YouTube that I can't do it while I'm zooming. We tend to crash everything, so I'm just waiting till the end.
Okay.
Yeah, they're all ready to go. All right, I will see you, man, in 2 hours. I'm gonna get these dogs out.
You
All right, we'll talk to you soon.
Thank you.
All right, bye-bye.